we start today's lesson, please write the rule for the reflection over each line that you see listed. Please try to do this without looking back at any notes to see what you already remember. So here are the 6 reflection rules that you are responsible for knowing. So 9.7 deals with tessellations. A tessellation, or sometimes referred to as a tiling, is just a repeating pattern of figures that completely covers a plane. So the fact that it covers a plane means it continues infinitely, and there are no gaps or overlaps within that tiling or that tessellation. The way that this fits in with what we were talking about is it is created with the isometries. So we need to think, what are the isometries that we know? So the isometries we know are translations, reflections, rotations, and glide reflections. So here we have examples of tessellations. This first one, I've already outlined the smallest repeating figure. If I outline anything else when I perform any type of isometry, I would end up with either a gap or an overlap, which is not allowed. So this one, in order to continue this pattern, we would need to perform a translation on this shape. So if I, see, there we go. If I translate this shape multiple times, and it doesn't have to be the same translation every time. So I've gone diagonal a couple of times, and then I can go horizontally. I could do vertical. And if I continue to do this, I would be able to cover that entire area. So take a second and outline or shade in what you think the smallest repeating figure is in the tessellation for part B. So for B, there's a couple of options that I've had students come up with in the past that I like. First one, the smallest, would be this red concave pentagon. So this concave pentagon, we could rotate around some different points. For example, if I rotate around that point that I just added, I would be able to fill in the next couple of sections. Now, if I change my center of rotation to, let's say, this black point that I'm adding, and I take that initial object and I rotate it so that that point is the one that is not moving, I would be able to fill in this other piece. So now if I just kind of repeat that, I would be able to fill in the rest of the tessellation. Some people will argue that it's too difficult to get the rest of the shape to fill in using that, so they look at this purple one, and they say, well, what if I use the purple one? Is that possible? Well, if you use that purple one and you rotate it around the center of that segment that I just added, meaning that's this piece that doesn't move, I would get this new shape. And if you look very closely, the lines would match up when you look at each individual pentagonal section. So now I always ask the question, how would you get then, if I took this purple one and continued it, how would I get other parts of the tessellation? Some people will inevitably say reflection. So I always challenge that by, this is easy to do with the smartboard here. If I reflect, I'll always say reflection. If I reflect over this vertical line, if you look closely, once I get this lined up, you won't have the smaller interior sections lining up. You can see the purple lines don't line up with the lines that are already printed. So a reflection would not be a correct option here. But I could do another rotation. I just changed the center of rotation to the midpoint of this line. I would be able to, here's that shape again, and if I rotated it around, it would end up matching just like we need. So again, changing centers of rotation would allow us to use rotations to perform this tessellation, excuse me. So here, if I start there, come on, and I rotate around this red point, that point would be there not moving, and it would match up with the section below. So this one would be rotations. Now C, again, take a second, either outline or shade in the repeating figure. So hopefully this is what you outlined or shaded in. Now this one, pretty straightforward in terms of tessellations. You can't rotate because then your objects won't match up. Oh man, this is not cooperating very well. Now if I move this, maybe not. You can see how it would start filling everything. This would be another example where a translation would be used. So more often what we focus on is the set of polygons that we've looked at. Might be a combination, it might be all the same. If we ever want to look and see whether a specific single type of polygon will be able to be tessellated, we need to see if the sum of the measures of the angles around any vertex, any single point, can add up to 360. That would ensure we wouldn't have any gaps and that we would not have any overlaps. To determine if you can use a single regular polygon to tessellate, you need to figure out whether or not each interior angle is a factor of 360 degrees. So if we want to find, let's say we call this A, if we want to find the measure of that interior angle, hopefully we remember back, be able to do this. The total number of degrees for all the interior angles would be 180 times n minus 2. But now if we just want to find one in a regular polygon, we don't divide by 2, we divide by n. Keep in mind, n represents the number of sides. And then similar to yesterday where we talked about being a factor of 180, this is going to be a factor of 360. If you take 360, you divide it by that angle measure, and you need to get a whole number. That says it would be a factor. So, can you make a tessellation using just 18 gons? So find the measure of one interior angle of an 18 gon. To do that, you have to take 180, multiply it by the quantity 18 minus 2, and divide it by 18. Well, if I just simplify this, 180 over 18 is really just 10. 18 minus 2 is 16. This is 160 degrees for one interior angle of regular 18 gon. So now, is that a factor of 360? 360 divided by 160 is 2.25. So it's not a factor. 160 is not a factor because that's not a whole number that we got when we did the division. So you cannot tessellate regular 18 gons. So to save us a little bit of time, there are a few shapes that can always tessellate no matter what. The first being triangles. So earlier this year we talked about why all the angles of a triangle add up to 180 degrees and how it's related back to alternate interior angles. But here you can see you've got the same triangles, and if you look closely around one point, you'll notice on one side of that you have the three different, if I number them in this triangle, you have the three different angles all connecting to that one point. So I have 3, then this one would be this angle 2, this would be angle 1. All 3 of those from a triangle have to add up to 180. The same would be the same on the opposite side. The second one that always can be tessellated is a quadrilateral. We know quadrilaterals always have interior angles that add up to 360 degrees. So again, if we look around one point and I number the angles of one specific quadrilateral, we would have around that one point, that'd be angle 2, this would be angle 1, and here would be angle 4. All 4 of those angles meet up and add up to 360 degrees just because of our knowledge about this quadrilateral's angles. So when we talk about tessellations, we also talk about the types of symmetry tessellations have. So the 3 types of symmetry we've already covered are reflectional symmetry, otherwise called line symmetry, rotational symmetry, which remember rotational number of degrees has to be less than 180, or point symmetry, which is rotational symmetry of exactly 180 degrees. So it's a special type of rotational symmetry that we have to list anytime it's there. But with tessellations, they also have translational symmetry, which would just mean you could continue the tessellation by translating the tessellation and everything would match up, or glide reflectional symmetry, where if you take a chunk of the tessellation and you perform a glide reflection on it, it would still match up onto itself. So our first tessellation, I've already gone ahead and outlined part of that tessellation for you, so we can see which types of symmetry it would have. So this would have translational symmetry, because if I were to just move this chunk of it, if I just translate it, this would match up with the rest of the tessellation. So if I translated it this way, or I could go back to the left, everything would match up. So this tessellation would have translational symmetry. But now I have to start looking at it. Can I rotate at all to the point where this will be matching up? So notice now I've rotated this 180 degrees. That would have point symmetry because I rotated 180 degrees. It's specifically point symmetry. Or if I do this, if I take this whole tessellation and I rotate the entire thing 180 degrees, you notice, and this isn't perfect, but if I were to fill this over, you kind of use your imagination, this would just be a continuation of the same pattern. So this first one has 2 different types. It has translational symmetry and point symmetry. The second one, a little bit more complicated. For this, we have to look at a combination of the 3 triangles, a big triangle, a medium-sized triangle, and a small triangle. So this again would have translational symmetry because I could just move this combination of 3 triangles using translations, any direction, any distance that I need, and it would all match up. But this would also have rotational symmetry because if I took this shape and I rotated it, I could, and again, I just went clockwise, let's go counterclockwise like we typically do. I could rotate it a certain number of degrees that would have everything still match up. So I didn't mention this in part A, and I should have, so I apologize, but we also should think about where would the centers of rotational symmetry be. Here, you could rotate about the center of each triangle. It doesn't matter which one, and you can do that for any of them. So let's say if I go back to my original, actually no, let's keep this way. If I rotate, let's say I rotate around the center of the smallest triangle, meaning that's the part that doesn't move. If I rotate, I would still be able to match up with the tessellation. So here's another way you can look at it, okay? Turning your paper. If it's not as easily done for you visually, try spinning your paper, okay? You're not going to have the benefit of having two to compare, but if I just rotate this, you can see that I do end up with the same pattern where I have a large triangle, and then on the lower left of it I have a small triangle, on the lower right of it I have a big triangle. Those two patterns match up, so it does have rotational symmetry. So if we go, let's go back to A for a second. Where would the centers of point symmetry be? Because remember, that is a type of rotational symmetry. You could actually center at a vertex. So I could center, you have to forgive the picture being a little bit off. I'll do this. Well, it might match up better. So I could have the center of rotation being at any of these vertices, or I could also have it be at a midpoint of any side. If I just rotate around that midpoint, this shape would be the result in green. All right, the final example was the most difficult out of these three. So I've already outlined one portion of this tessellation in green. So this, if I were to translate, would match up. Okay, it would translate onto itself. So this has translational symmetry. If I take this and I rotate it, at any point, am I able to get it to look the exact same? Oh, right there. Oops, come on. Right there, it would be the exact same. So that would be point symmetry, and one of the centers of rotation would be the midpoint of that center segment, or we could rotate around midpoints of those outside two segments. I wonder, let's check, can we rotate around this point? Let's check that. So if I rotate 180 degrees, and then I have that point remain the same, yep, so that would be another one. So we could also rotate around any of those. So the same thing would happen here, here, and there. So now we need to look at, does it have reflectional symmetry or line symmetry? Can you draw a line in here that would be a line of symmetry? If I were to reflect over that line or fold across that line, would everything match up? It would, so this would be an example of a line of reflection it would have. So it would have reflectional symmetry. And it would also have glide reflectional symmetry. If I took this original shape that I had outlined, move it, excuse me, and then reflect it over that line of reflection that I have, where is it? There we go. It would end up there. So again, it matches up. So in review, C has reflectional symmetry. It has point symmetry, glide reflectional symmetry, and translational symmetry. It's got 4 out of the 5. Let's check and see, is there any just regular rotational symmetry? So to do that, I'm going to take this and I'm going to rotate it and see if at any point does it match up perfectly with the pattern that I already have. So now this kind of might play tricks on your eyes a little bit, but that is the same pattern. It looks different because of the outline that you have right now. But I could show this. If I come over here, let me clean this one up a little bit. If I come over here and I outline that shape, would match that shape. So this would also have rotational symmetry. It's got all 5 types of symmetry: translational, rotational, point, what am I forgetting? Glide reflectional symmetry, and just regular reflectional symmetry. I don't know if I mentioned that one or not. So again, translational, rotational, point, reflectional symmetry, and glide reflectional symmetry. Now, how can you use an arrangement, so a combination of regular 12-gons, so dodecagons, and equilateral triangles to tessellate a plane? So you have to remember, in order to tessellate, you have to get exactly 360 degrees around a single point. So all the way around here, terrible circle, I know. I need 360 degrees to fill it in perfectly. So what you need to think about are the angles of each shape. So the angle of an equilateral triangle and the regular dodecagon. So right now, figure out what each of those angle measures would be for an interior angle. Hopefully we all know that equilateral triangles are also equiangular, so that is 60 degrees. Then if I actually calculate out regular dodecagon, I would end up with 150 degrees. Is it possible to use those two numbers to come up with exactly 360 degrees? Well, if I use one equilateral triangle and I use 2 dodecagons, that gets me exactly 360 degrees. So you'd have to write out that you'd have 2 dodecagons and 1 equilateral triangle meeting at each vertex in order to perform a tessellation. So here I've gone ahead and actually made part of a tessellation that includes dodecagons and equilateral triangles. And you can see around any single point, any single vertex, what objects are meeting there. I have 2 dodecagons and an equilateral triangle. It fills up that entire 360 degrees. Same thing at each of these vertices where the polygons all intersect. So if any part of this was confusing to you, please go back and rewatch whatever part of the video you need. Otherwise, you can ask me questions. But now, please, if there's any time left, go ahead and get started with your homework.